October 12, 1943. 32,000 feet above Münster, Germany. Lieutenant Werner Streib watched through his canopy as the massive formation of American B-17s droned steadily toward their target, their contrails painting geometric patterns across the autumn sky. As Staffelkapitän of the 2nd Staffel, Jagdgeschwader 1, Streib had developed a hunter's patience during 2 years of combat against British bombers. He studied the American formation with professional detachment, counting aircraft, noting their altitude, calculating approach vectors. His Messerschmitt Bf-109 G6 climbed steadily toward the bomber stream, the Daimler-Benz DB605 engine pulling him upward through the crystalline air. At this altitude, nearly 6 miles above the earth, the cockpit was bitterly cold despite his heated flight suit. Oxygen hissed through his mask with each breath. Below him, stretched across 20 miles of sky, 40 Messerschmitt 109s from Jagdgeschwader 1 and Jagdgeschwader 26 climbed to intercept. Then Streib saw them. High above the bombers, perhaps 2,000 feet higher than his own altitude, a formation of 8 American fighters circled lazily. Even at this distance, their silhouettes were unmistakable. Barrel-shaped fuselages, enormous radial engines, wings that seemed absurdly small for their massive bodies. Streib permitted himself a slight smile. The Americans had positioned their escorts above the bombers, correct doctrine, but at an altitude where their heavy fighters would be sluggish and unresponsive. He transmitted to his formation, maintaining the calm, professional tone expected of a Staffelkapitän. Achtung! 8 Thunderbolts at angles 3 to 4, positioned high. We will attack the bombers from below. If the Americans dive, break, and dive with them. Their fat fighters cannot follow us down, his pilots acknowledged with brief clicks of their radio transmitters. This was standard procedure, tactics they had practiced against the heavy American fighters for months. The Messerschmitt 109's greatest advantage was its diving speed. When pressed by enemy fighters, German pilots could simply push their control sticks forward and dive away at speeds approaching 500 miles per hour. The pursuing aircraft, whether British Spitfires or American Thunderbolts, would fall behind as German fighters accelerated beyond their limits. What Streib didn't know, what none of the German pilots climbing toward the bomber stream could have imagined, was that the physics of high-speed flight were about to demonstrate a terrifying truth. The aircraft he had just dismissed as too fat to dive was capable of reaching 550 miles per hour in a vertical plunge, while maintaining control that would allow it to pull out of dives that would tear apart every German fighter in the sky. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within minutes, Streib would discover that the tactical doctrine his entire fighter force relied upon for survival had become a death sentence. The mathematics of destruction were already in motion, governed by laws of aerodynamics and structural engineering that German aircraft designers had never fully solved. This is the story of how American engineering created an aircraft that could dive faster than the sound barrier would allow, how German interceptors discovered that their standard escape maneuver had become a suicide tactic, and how the Republic P-47 Thunderbolts' ability to survive terminal velocity dives transformed it from a defensive escort into an offensive predator that owned the vertical dimension of aerial combat. The story begins not in the skies over Germany, but in the engineering halls and wind tunnels where Alexander Kartveli, Republic Aviation's Georgian-born chief designer, wrestled with a problem that seemed to defy solution. When the United States Army Air Corps issued specifications for a high-altitude interceptor in June 1940, they demanded performance that exceeded every existing fighter. Speed, altitude, firepower, range, every parameter pushed beyond known limits. Kartveli understood that meeting these requirements would require an aircraft larger and heavier than any single-engine fighter ever built. Size meant weight. Weight meant massive power requirements. Massive power meant an enormous engine. The Pratt & Whitney R2800 Double Wasp, an 18-cylinder radial producing 2,000 horsepower, became the heart of Kartveli's design. But installing this engine created cascading engineering challenges. The radial engine required a large diameter fuselage to accommodate its width. The turbo supercharger system, essential for high-altitude performance, needed complex ducting running through the rear fuselage. This gave the aircraft its distinctive pregnant appearance, with the fuselage swelling behind the cockpit to house exhaust ducts, intercoolers, and the massive turbo supercharger itself. Early in the design process, Kartveli recognized a fundamental problem. An aircraft this large and heavy would generate enormous speed in dives. Basic physics dictated that a 7-ton fighter falling from 30,000 feet would accelerate to velocities that most aircraft could not survive. The P-47 would need structural strength far exceeding normal fighter requirements. Republic's engineering team began calculations that would define the Thunderbolts' most remarkable characteristic. They determined that the aircraft's wing structure needed to withstand loads of 12 times the force of gravity. Most fighters of the era were built to handle 6 to 8 G loads. The P-47 would be built to survive forces that would literally tear pilots unconscious before the aircraft failed. The wing spars, the main structural members running the length of each wing, were machined from solid aluminum forgings. Each spar could support loads exceeding 20,000 pounds. The wing ribs, the curved members that gave the wing its aerodynamic shape, were reinforced with additional bracing. Skin thickness was increased beyond normal specifications. The resulting wing structure weighed nearly 2,000 pounds, heavier than entire aircraft from the previous war. Fuselage structure received similar attention. 4 massive longerons, aluminum tubes running the length of the fuselage, formed the primary load-bearing structure. These were connected by bulkheads and formers built to withstand crushing forces. The engine mount, supporting a 2,000 horsepower radial that generated tremendous vibration and torque, was constructed from steel tubing capable of handling 12G impacts. When the XP-47B prototype first flew on May 6, 1941, test pilot Lowry Brabham immediately noticed the aircraft's unusual flying characteristics. It was heavy on the controls, requiring significant force to move the stick, but it felt solid, planted, unshakable. During early test flights, Brabham discovered something unexpected. The P-47 dove like nothing he had ever flown. Republic's test program included extensive dive tests to verify structural integrity. Brabham would climb to 25,000 feet, roll inverted, and pull the stick back, pointing the massive fighter straight down. The Thunderbolt would accelerate with enthusiasm that bordered on alarming. The airspeed indicator needle would swing past 300 miles per hour, then 350, 400, 450. At 500 miles per hour, something strange began happening. The controls would stiffen, becoming progressively harder to move. The aircraft would begin buffeting, shaking violently. Brabham would try to pull back on the stick to begin recovery, but the control forces exceeded his strength. The aircraft continued diving, accelerating toward a speed that would end in a smoking crater. What Brabham was experiencing was compressibility, a phenomenon that would not be fully understood until after the war. As the Thunderbolt approached the speed of sound, roughly 760 miles per hour at sea level, but significantly less at altitude, the air flowing over the wings began forming shock waves. These shock waves changed the pressure distribution over the wing surface, moving the center of lift and creating a powerful nose-down pitching moment. The effect was like having an invisible hand pushing the aircraft's nose toward the ground with tremendous force. Pilots had to pull back on the control stick with both hands, using all their strength to overcome this compressibility tuck and begin recovery. Many pilots couldn't generate sufficient force and either rode the dive all the way to ground impact or bailed out, abandoning aircraft that might have recovered if they'd been stronger. Republic Aviation recognized that compressibility represented a potentially fatal flaw. If pilots couldn't recover from high-speed dives, the aircraft was useless in combat. Engineers devised a solution that seemed almost crude, but proved remarkably effective. They installed dive recovery flaps, small hydraulically operated surfaces mounted under each wing near the trailing edge. When a pilot encountered compressibility and couldn't overcome control forces through muscle power alone, he could flip a switch, activating these dive flaps. The flaps would extend into the airstream, creating additional downward force on the tail and helping to pitch the nose up. The system worked, though it added complexity and weight to an already heavy aircraft. Testing revealed another characteristic that would prove crucial in combat. When pulled out of high-speed dives, the P-47 could sustain G-forces that would cause other fighters to shed wings or tail surfaces. Test pilots routinely pulled 8, 9, even 10 Gs during recovery maneuvers. The aircraft groaned and creaked, rivets strained, but the structure held. Lieutenant Colonel Mark Bradley, assigned to right field to evaluate the P-47 for combat suitability, conducted extreme dive tests in early 1942. Bradley would climb to 35,000 feet, enter a vertical dive, and accelerate past 500 miles per hour. At 10,000 feet, he would activate the dive recovery flaps and begin pulling back on the stick with both hands braced against his knees for leverage. The G-forces would slam him down into his seat with crushing pressure. His vision would narrow to a tunnel, then grey out completely as blood drained from his brain. He would maintain back pressure on the stick, unconscious, until the aircraft leveled off on its own or he regained consciousness at a safe altitude. The Thunderbolt would pull out successfully, every time. Bradley's report to the Army Air Forces was unequivocal. The P-47 could dive faster and pull out more reliably than any fighter he had tested. The first operational P-47s reached England in December 1942. The 56th Fighter Group, based at Kingscliff, began combat operations in April 1943. Early missions revealed what German pilots had already observed. The Thunderbolt climbed poorly, turned sluggishly, and handled like a truck at medium altitudes. German fighter pilots quickly developed tactics to exploit these weaknesses. Oberle, Lieutenant Egon Meyer, commanding officer of Jagdgeschwader II, pioneered the head-on attack against American bomber formations. This tactic brought his fighters through the bomber stream at closing speeds exceeding 600 miles per hour, too fast for bomber gunners to track. After firing, Meyer's pilots would simply dive away, accelerating beyond the range where escorting Thunderbolts could follow. By May 1943, this tactic had become standard throughout the Luftwaffe fighter force. Attack bombers from any angle, but always disengage by diving. The heavy American escorts couldn't follow a diving Messerschmitt or Focke-Wulf. German pilots who needed to escape combat had a simple, reliable procedure: push the stick forward, dive, and accelerate away. The tactics worked brilliantly through spring and early summer 1943. American bomber losses climbed. Fighter groups filed reports describing German fighters diving away from combat, untouchable, unreachable. The Thunderbolt's reputation as a defensive escort suffered. Some commanders questioned whether the aircraft should remain in frontline service. Then American pilots began discovering the Thunderbolt's hidden strength. The aircraft that couldn't chase diving German fighters at medium altitude became a terror when starting from high altitude with energy advantage. The transformation began in June and July 1943, as experienced pilots developed tactics to exploit the Thunderbolt's diving capability. Major Hub Zemke, commanding the 56th Fighter Group, was among the first to recognize the tactical opportunity. Zemke understood that while the Thunderbolt couldn't catch a diving Messerschmitt when both aircraft started at the same altitude, physics changed dramatically when the Thunderbolt began 2,000 or 3,000 feet higher. Zemke organized training missions teaching his pilots to maintain altitude advantage, to position above German fighters before engaging. When German aircraft appeared below, Thunderbolt formations would roll inverted and dive, building speed rapidly. The massive fighters would accelerate past 400 miles per hour, then 450, approaching 500 miles per hour in steep dives. At these velocities, overtaking diving German fighters became not just possible but inevitable. The Thunderbolt's superior weight, gravity's ally in the dive, gave it acceleration that lighter German fighters couldn't match. Moreover, the P-47's structural strength allowed it to maintain control at speeds where German fighters encountered fatal limits. Captain Walker Bud Mahurin of the 56th Fighter Group developed what became known as the boom and zoom tactic, though pilots simply called it Thunderbolt diving. Mahurin would lead his flight to 30,000 feet or higher, climbing into the thin air where the turbo-supercharged double Wasp engine maintained full power while German fighters gasped for oxygen. When enemy fighters appeared below, often engaged with bombers at 24 or 25,000 feet, Mahurin's flight would roll inverted and dive nearly vertically. The Thunderbolts would accelerate to speeds approaching 550 miles per hour, faster than any German pilot had experienced in combat. German fighters, seeing American aircraft diving from above, would often attempt their standard escape maneuver, pushing into their own dives to accelerate away. This is where physics betrayed them. The Messerschmitt Bf 109, designed for agility and climb rate, had a relatively light wing structure optimized for moderate G-loads. The Focke-Wulf Fall 190, though more robust, still followed conventional fighter design philosophy, emphasizing maneuverability over structural strength. Both German fighters could reach speeds around 480 to 500 miles per hour in vertical dives from high altitude, impressive velocities that exceeded most Allied fighters. But at these speeds, approaching the edge of compressibility, both aircraft encountered control problems that German pilots had never fully solved. The Messerschmitt 109's control surfaces would flutter and vibrate. Pilots described the stick shaking violently, the aircraft buffeting as if flying through turbulent air. Attempting to pull out of dives at speeds exceeding 470 miles per hour required tremendous strength, and even then, the aircraft often wouldn't respond properly. The nose would stay down, locked in a terminal dive, or the wings would begin twisting under aerodynamic loads they weren't designed to handle. The Focke-Wulf 190 handled high-speed dives better than the Messerschmitt, but still encountered severe problems above 480 miles per hour. The radial engine installation, with its large frontal area, created additional drag that limited terminal velocity. More critically, the wings would begin twisting under load, changing their angle of attack in ways that made control nearly impossible. German test pilots had documented these limits in technical reports. Luftwaffe training emphasized that pilots should not exceed specific dive speeds. For the Messerschmitt 109 G series, maximum permissible dive speed was listed as 460 miles per hour indicated airspeed. For the Focke-Wulf 190A series, the limit was 475 miles per hour. Exceeding these speeds risked structural failure or loss of control. But combat created situations where desperate pilots exceeded limits trying to survive. Throughout 1942 and early 1943, Luftwaffe units recorded numerous accidents where fighters dove into the ground during combat, unable to pull out. Investigation often revealed that pilots had exceeded maximum dive speeds while attempting to evade pursuing British or American fighters. The solution was simple: don't dive that fast. Maintain control by limiting speed, accept reduced performance, survive to fight another day. This worked acceptably well through early 1943 because British Spitfires and early-model American fighters had similar dive speed limitations. Everyone was constrained by similar physics. The P-47 changed this equation fundamentally. When Thunderbolts began diving from altitude advantage, reaching speeds of 520, 530, 540, even 550 miles per hour, they were operating in a velocity range where German fighters literally could not compete. German pilots attempting to escape by diving found themselves caught in an impossible situation. They would push into their maximum speed dives, reaching 470 or 480 miles per hour, the limit of their aircraft's capabilities. Behind them, Thunderbolts would continue accelerating, closing the distance with mathematical certainty. Trying to pull out was equally futile. German fighters at maximum dive speed required thousands of feet to recover, pulling enormous G-loads that left pilots unconscious or barely conscious. Thunderbolts could dive past them, pull out below them with brutal G-forces that merely compressed American pilots into their seats without causing loss of consciousness, then climb back up for another attack. The event that would demonstrate this capability most dramatically occurred on August 17, 1943, during the dual raids on Schweinfurt and Regensburg. This mission, the deepest penetration into Germany attempted to that date, would reveal both the P-47's limitations in range and its terrifying effectiveness when employed from altitude advantage. Major David Schilling, leading the 62nd Fighter Squadron of the 56th Fighter Group, climbed his formation to 32,000 feet near the German border. Below, massive formations of B-17s droned toward their targets. Schilling's 16 Thunderbolts circled high above, guarding against German fighters that intelligence predicted would attack in force. The prediction proved accurate. At 09:45 hours, Schilling spotted a formation of approximately 40 Messerschmitt 109s climbing from the south, angling toward the bomber stream. The German fighters were at 28,000 feet, still climbing, unaware of the American fighters positioned 4,000 feet above them. Schilling transmitted brief instructions to his squadron. Diving. Attack on 109s below. Stay in formation. Don't chase into the deck. He rolled his Thunderbolt inverted, pulled the stick back, and pointed his aircraft straight down at the climbing German fighters. The other 15 Thunderbolts followed in perfect formation, a diving wall of American steel and firepower. The massive radial engines roared as propellers bit into thin air. Airspeed indicators began climbing, 300 miles per hour, 350, 400. The dive steepened, 420, 440, 460. Below, German pilots spotted the diving Americans but weren't initially concerned. American fighters diving from altitude was standard tactics. The solution was equally standard: push into your own dive, accelerate away, break contact. Multiple Messerschmitt pilots pushed their sticks forward and began their escape dives. This is where the mathematics of destruction took over. The German fighters, starting at 28,000 feet and diving at approximately 45 degrees, accelerated rapidly to around 460 miles per hour. This was near maximum safe dive speed for the Messerschmitt 109 G6. Faster meant losing control or structural failure. The Thunderbolts, starting 4,000 feet higher and diving more steeply, were approaching 500 miles per hour and still accelerating. Weight advantage became decisive. Each P-47 weighed roughly 13,500 pounds fully loaded. Each Messerschmitt weighed approximately 7,000 pounds. In a dive, where gravity was the primary accelerating force, the heavier aircraft accelerated faster and reached higher terminal velocity. Schilling's gun sight tracked the lead Messerschmitt as the range closed with startling rapidity. At 800 yards, he could see the German pilot's head turning, looking back over his shoulder, recognizing the pursuing American was gaining despite being in a maximum speed dive. At 600 yards, the German began pulling back on his stick, trying to start recovery before the Thunderbolt could close to gun range. The Messerschmitt's nose began rising, but slowly, reluctantly. At 480 miles per hour, the 109's elevator effectiveness was severely reduced by compressibility effects. The aircraft needed significant altitude to complete recovery. Schilling closed to 400 yards, centered the illuminated pipper of his 9-gun sight on the German fighter's fuselage, and pressed the trigger. All 8 Browning M2 heavy machine guns fired simultaneously. At a combined rate of fire approaching 6,400 rounds per minute, the weapons created a stream of half-inch projectiles that converged at the range where Schilling had set his gun convergence, approximately 300 yards. The German fighter flew directly into this cone of destruction. Armor-piercing incendiary rounds, designed to penetrate armor plate then ignite after penetration, tore through the Messerschmitt's tail surfaces, fuselage, and wing roots. The aircraft came apart in mid-air, not gradually but catastrophically. The tail separated completely. Both wings folded upward, then ripped away. The engine and cockpit section tumbled separately toward Earth. No parachute appeared. The engagement lasted perhaps 4 seconds from the moment Schilling opened fire until the Messerschmitt ceased to exist as an aircraft. Across the battle space, similar scenes played out as other Thunderbolt pilots caught diving German fighters and destroyed them with concentrated machine gun fire. Lieutenant Robert Johnson, flying on Schilling's wing, encountered a Messerschmitt pilot who recognized the danger and tried a desperate maneuver. Instead of diving away, the German pulled into a climbing turn, attempting to use the 109's superior maneuverability at lower speeds to evade. Johnson, diving at over 500 miles per hour, could not follow the climbing turn. His Thunderbolt's massive momentum carried him past the German fighter, but Johnson understood the tactic. He extended his dive, building even more speed, then pulled back hard on the control stick. The G-forces slammed him down into his seat with crushing pressure. His vision grayed, then darkened to a narrow tunnel. He maintained back pressure, trusting the Thunderbolts' structure to handle loads that would tear apart lighter fighters. The aircraft groaned and creaked. The airframe flexed, but it held together. Johnson's dive flattened into level flight, then transitioned into a zoom climb. He pulled the nose up steeply, trading his enormous kinetic energy for altitude. The Thunderbolt rocketed upward, climbing at an angle that seemed impossible for such a heavy aircraft. Above him, the Messerschmitt pilot who had climbed to evade was now at a disadvantage. His aircraft had burned energy in the climbing turn and was moving relatively slowly. Johnson's zooming Thunderbolt, converting 500 miles per hour of dive speed into vertical climb, rose through the German fighter's altitude, with speed still in reserve. Johnson leveled off slightly above and behind the Messerschmitt, now at reduced speed, but in perfect firing position. The German pilot, seeing the American fighter impossibly positioned above him after having been in a dive moments earlier, hesitated for perhaps half a second, unable to process what his eyes were reporting. That hesitation was fatal. Johnson fired a 2-second burst. The Messerschmitt exploded. Major Schilling's squadron claimed 14 Messerschmitts destroyed in approximately 6 minutes of combat. Post-mission analysis revealed that 12 of these were destroyed in diving attacks where German pilots had attempted to escape using their standard dive-away tactic. 2 were destroyed in zoom climb maneuvers after initial diving attacks. The 56th Fighter Group lost 0 aircraft. German pilots surviving the engagement filed combat reports that revealed profound confusion. Multiple pilots described American fighters diving at unbelievable velocities, catching Messerschmitts in maximum speed dives. Several reports mentioned Americans pulling out of dives far too quickly to be possible, suggesting their aircraft possessed some new technology. Luftwaffe intelligence officers reviewing these reports initially dismissed them as pilot exaggeration under combat stress. American Thunderbolts had definite performance limitations that German pilots understood well. The idea that these heavy fighters could dive significantly faster than German aircraft seemed to contradict known physics. But similar reports accumulated through late August and September 1943. Multiple pilots from different units described the same phenomena. American fighters diving from high altitude would catch German fighters attempting to escape. Americans would pull out of dives at altitudes where German pilots would expect them to crash, then zoom climb back into combat with energy still available. By October 1943, Luftwaffe intelligence began taking these reports seriously. They ordered technical analysis of captured or shot down P-47 aircraft to understand what allowed these performance characteristics. The investigation revealed engineering decisions that German designers had not pursued. When German engineers examined P-47 wreckage recovered from crashed aircraft, they were astonished by the structural overbuilding. Wing spars were far heavier than necessary for normal fighter operations. Fuselage longerons were massively oversized. Control surface hinges and actuators were built to withstand loads far exceeding what German fighters experienced. The full realization struck German engineers examining a relatively intact P-47 that crash-landed near Oldenburg in November 1943. The pilot had been killed, but the aircraft structure remained largely complete, allowing detailed inspection. Metallurgical analysis of wing spar samples revealed aluminum alloys heat-treated for maximum strength, then machined to precise dimensions that maintained strength while minimizing weight. Stress analysis calculations showed the wing structure could theoretically handle sustained loads of 12 Gs. Fuselage structure was similarly overbuilt. The engineering represented a fundamental philosophical difference. German fighters were built to minimum specifications necessary to meet performance requirements, optimizing weight efficiency. The Thunderbolt was built to survive conditions far beyond normal operations. The German Technical Intelligence Report concluded that American designers had created a fighter that could operate in flight regimes where normal aircraft would fail catastrophically. The report recommended that Luftwaffe pilots be warned that diving away from P-47s was no longer a reliable escape tactic, particularly when American fighters held altitude advantage. This recommendation reached operational units in early 1944, but implementation proved nearly impossible. Diving away was ingrained behavior developed over years of combat. Pilots who had survived dozens or hundreds of combat missions by diving to escape could not easily abandon tactics that had kept them alive. More fundamentally, Luftwaffe pilots had no alternative evasion tactic that worked reliably against Thunderbolts. They couldn't outclimb the turbo-supercharged Americans at high altitude. They couldn't outturn them in sustained combat without burning dangerous amounts of fuel. Diving had always been the reliable escape. Now, that was gone. The psychological impact was profound. German fighter pilots began experiencing what medical officers termed Höchangst, altitude fear. Pilots who had previously operated confidently at 30,000 feet or higher now reported anxiety when American fighters were positioned above them. The knowledge that diving no longer guaranteed escape created stress that affected combat performance. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Statistical evidence supported what combat reports described. In the fourth quarter of 1943, P-47 units achieved a kill ratio of 2.8 to 1 against German fighters. More significantly, analysis of combat losses revealed that Thunderbolt losses to enemy fighters dropped by 37% compared to the previous quarter, despite flying deeper into Germany against increasing German resistance. The reduction correlated directly with increased use of high-altitude tactics, exploiting the Thunderbolt's diving capability. Fighter groups that consistently maintained altitude advantage and employed diving attacks from above showed the most dramatic improvements in both kill ratios and survival rates. Major Hubert Zemke, now commanding the 56th Fighter Group with the rank of colonel, issued tactical guidance in January 1944 that codified lessons learned over the previous 6 months. The document, distributed throughout 8th Air Force fighter groups, emphasized altitude advantage as the primary tactical consideration. Zemke's guidance stated explicitly, "The P-47's greatest advantage is its ability to dive faster and pull out more reliably than any German fighter. Maintain altitude. Force the enemy to climb to you. When they attempt to escape by diving, follow them down and destroy them. Your aircraft can reach speeds they cannot survive. Your structure can handle recovery, G-loads that will tear their aircraft apart." This represented a complete inversion of previous fighter doctrine. Traditional thinking emphasized maneuverability, climb rate, and sustained turn performance. Zemke's approach treated the fighter as a high-altitude platform for delivering kinetic energy weapons. The aircraft itself became the weapon, diving at terminal velocity to intercept targets that couldn't escape. Implementation required retraining pilots to trust their aircraft in situations that seemed suicidal. Diving vertically at 500 miles per hour toward the Earth, watching the ground rush up with terrifying speed, every instinct screamed to pull out early, to recover while altitude remained. But early recovery meant losing the speed advantage, allowing German fighters to escape. Effective Thunderbolt tactics required pilots to maintain their dives until reaching firing range, typically 400 to 300 yards, then opening fire while still in the dive. Only after confirming hits or determining the target had been destroyed would pilots begin recovery, pulling back on the stick with both hands, enduring crushing G-forces, trusting the airframe to handle loads that would fold other aircraft like paper. Lieutenant Eugene Valencia, assigned to the 56th Fighter Group in February 1944, described his first high-speed diving attack in a letter home that survived in his personal papers. "We were at 31,000 feet when we spotted Jerries below attacking bombers. Colonel Zemke ordered us to attack. I rolled inverted and pulled back on the stick. The nose dropped toward vertical. The earth rushed up like I was falling off a building. The airspeed needle climbed past 400, then 450, then 500. The aircraft was shaking, vibrating like it was going to come apart. I thought I was going to die, but I kept the dive, kept the nose down, watching the German fighter grow in my gun sight. At 400 yards, I opened fire. My guns were only on target for maybe 1 second before I had to start pulling out. I pulled back on the stick with both hands. Nothing happened. The stick wouldn't move. I pulled harder, using my knees braced against the instrument panel for leverage. The stick moved maybe an inch. The G-forces hit like a truck. Everything went grey, then black. I couldn't see anything, but I kept pulling on that stick. When my vision came back, I was in a climb, still going 300 miles per hour. The German fighter was gone, just pieces falling. I'd hit him in that 1-second burst and he'd come apart. Later they told me I pulled almost 11 Gs in that recovery. I should have been unconscious, but somehow I stayed aware enough to keep pulling. The aircraft didn't even creak, just pulled out like it was built for it, which I guess it was. Valencia survived the war with 9 confirmed victories, all achieved using diving attacks from altitude. He credited the P-47's structural strength with saving his life on multiple occasions when he misjudged recovery timing and pulled excessive G-loads that would have destroyed lighter fighters. German fighter pilots who survived encounters with diving Thunderbolts consistently described the experience as terrifying. Oberfuhrer Gunther Roll, commanding officer of Jagdgeschwader 11, with 275 confirmed victories, encountered Thunderbolts employing high-altitude diving tactics during a mission near Magdeburg on March 11, 1944. Roll, flying a Messerschmitt Bf 109 G6, had just attacked a formation of B-17s when his wingman called out American fighters diving from above. Roll looked up to see 4 Thunderbolts in a nearly vertical dive, already traveling at what he estimated was well over 500 miles per hour. They were 3,000 feet above him and closing with impossible speed. Roll executed standard evasion, pushing into his own maximum speed dive. His Messerschmitt accelerated rapidly, reaching 460 miles per hour within seconds. He glanced back, expecting to see the heavy American fighters falling behind. Instead, they were closer, still in their vertical dives, still accelerating. The lead Thunderbolt was perhaps 600 yards behind and gaining rapidly. In a post-war interview conducted by American military historians in 1953, Roll described what happened next. I was in a maximum dive, my aircraft shaking violently, flying at the edge of what was safe. The American was diving faster, catching me. This should not have been possible. I thought perhaps he would dive past me and crash, but at perhaps 400 yards, he opened fire while still in his dive. I saw his tracers, streams of them, hundreds of bullets. I broke left as hard as I could. The G-forces nearly made me black out. Some of his bullets hit my aircraft. I heard them, felt impacts. But the brake saved me. He could not follow my turn at that speed. He went past me, diving at what must have been 520 or 530 miles per hour. I thought he would crash. No aircraft could pull out from that speed at that altitude. We were perhaps 8,000 feet above ground, but he pulled back on his stick and his aircraft began recovering. I watched, disbelieving. The Thunderbolt pulled perhaps 10 or 11 Gs. You could see the wings flexing, bending upward under the load. Any normal fighter would have shed its wings. His aircraft just pulled out, flattened into level flight, then climbed away. At that moment, I understood we were facing something unprecedented. The Americans had built a fighter that could dive faster than we could fly and pull out from dives that would kill us. This changed everything. The tactic we had used for 4 years to survive was no longer viable. If you dove to escape a Thunderbolt, you were simply choosing the manner of your death. Either he would catch you in the dive and shoot you, or you would crash trying to pull out at his speed. The technical explanation for the Thunderbolt's diving capability lay in Republic Aviation's engineering philosophy and the specific design choices Alexander Kartvel's team had made. The massive wing structure, criticized by some as overweight and inefficient, provided the strength necessary to survive terminal velocity dives and high G recoveries. Each wing was built around a main spar machined from a solid aluminum alloy forging. This spar, running from fuselage attachment point to wing tip, was dimensioned to handle a braking load of approximately 40,000 pounds. The P-47's maximum gross weight was roughly 13,500 pounds. The safety factor was nearly 3-to-1, far exceeding normal fighter design practice. The wing ribs, the curved members that shaped the airfoil cross-section, were stamped from aluminum sheet, then reinforced with additional gussets and doublers at high-stress locations. The wing skin itself was thicker than standard practice required, adding weight but providing additional strength and resistance to aerodynamic flutter at high speeds. Control surfaces received similar attention. The elevators, critical for recovery from high-speed dives, were built with heavy-gauge aluminum ribs and spars. The control horns, which connected the elevator surface to the control cables, were forged steel rather than aluminum, capable of transmitting enormous forces without failure. The dive recovery flaps, installed on production aircraft beginning with the P-47D model in late 1942, provided additional margin when pulling out of extreme dives. These small flaps, mounted under each wing near the trailing edge, could be deployed hydraulically by the pilot when encountering compressibility effects that stiffened the controls. When deployed, the dive flaps extended approximately 6 inches into the airstream, creating additional downward force on the tail. This helped pitch the nose up, assisting the pilot in overcoming compressibility-induced control forces. The system added complexity and weight, but provided the capability to recover from dives that would otherwise be unrecoverable. German designers were aware of compressibility problems, but approached solutions differently. The Messerschmitt design team, led by Willy Messerschmitt, emphasized lightweight and aerodynamic efficiency. Their solution to dive limitations was to impose speed restrictions and train pilots to respect those limits. This worked adequately in the context of combat against similarly limited opponents. The Focke-Wulf design team, under Kurt Tank's leadership, pursued somewhat higher structural strength for the W190, but still within conventional fighter parameters. The 190 could dive faster than the Messerschmitt 109, reaching approximately 480 miles per hour before encountering severe compressibility effects, but this still fell far short of the Thunderbolts' capabilities. Neither German design team pursued the brute force over-engineering approach that Republic Aviation employed. The German philosophy emphasized doing more with less, creating efficient designs that met requirements with minimum weight. This approach worked well for many applications, but left German fighters unable to compete in the high-speed dive regime where physics favored heavy, overbuilt structures. By spring 1944, Luftwaffe fighter units were suffering unsustainable losses. Statistics compiled by the Reichsluftfahrtministerium, the German Air Ministry, showed fighter losses had increased 42% between the fourth quarter of 1943 and the first quarter of 1944. Analysis of loss reports revealed that a significant percentage of these losses occurred during attempted dive escapes from American fighters. The German response combined tactical adaptation with attempts at technical solutions. Luftwaffe fighter tactics evolved to emphasize avoiding situations where American fighters held altitude advantage. This meant attacking bombers from below or from the same altitude, never from above where Thunderbolts could dive on German fighters from higher altitude. But this tactical constraint created its own problems. Attacking from below exposed German fighters to concentrated fire from bomber defensive formations. Messerschmitts and Focke-Wulfs, making climbing attacks from underneath B-17 formations, faced fire from dozens or hundreds of 50-caliber machine guns. Loss rates in these attacks were catastrophic. Attacking from co-altitude reduced exposure to bomber defensive fire, but meant German fighters were more vulnerable to escort fighters. Without the ability to attack from above, dive through the bomber stream, and escape downward, German pilots had to remain near bomber altitude where American escorts could engage them directly. Some Luftwaffe units experimented with specialized tactics designed to counter the Thunderbolts' diving advantage. One approach involved using formations of fighters as bait to draw American escorts into diving attacks, while additional German fighters positioned at very high altitude, above even the Thunderbolts, would dive on the Americans from above. This tactic worked occasionally but required precise coordination and numerical superiority. By mid-1944, the Luftwaffe rarely had sufficient fighters available for such complex operations. More typically, German fighters were outnumbered and forced to engage under unfavorable conditions. Technical solutions pursued by German designers focused on developing fighters with better high-speed characteristics. The Messerschmitt Me-262 jet fighter, entering service in small numbers in mid-1944, could dive at speeds exceeding 550 miles per hour without encountering compressibility effects. But jet fighters remained rare, complex, and operationally limited. Attempts to improve conventional piston engine fighters met limited success. The Focke-Wulf TAR-152, a high-altitude development of the FW-190, featured strengthened wings and improved high-speed handling. but production delays and material shortages limited deployment. Most Luftwaffe units continued flying Messerschmitt 109s and Focke-Wulf 190s with the same limitations that had made them vulnerable to diving Thunderbolts. The D-Day invasion on June 6, 1944, demonstrated how completely American fighters had achieved air superiority over Europe. Luftwaffe fighter forces, already depleted by months of attrition, were virtually absent from the skies over Normandy. The few German fighters that attempted to interfere with the invasion were quickly destroyed by overwhelming numbers of Allied fighters, many of them Thunderbolts, employing the high-altitude diving tactics that had proven so effective. In the months following D-Day, P-47 units increasingly focused on ground attack missions, using their diving capability to deliver bombs and rockets with devastating accuracy. The same structural strength that allowed survival of high-speed air-to-air combat dives enabled Thunderbolts to attack ground targets in steep dives, release weapons, and pull out under heavy anti-aircraft fire. But aerial combat continued, particularly over Germany, as Allied bombers penetrated deeper into the Reich. Thunderbolt pilots continued exploiting their aircraft's diving advantage whenever possible. The kill ratio remained heavily in favor of American fighters through the summer and fall of 1944. Lieutenant Colonel Francis Gaby Gabreski, the leading American ace in Europe flying P-47s, achieved 28 confirmed victories before being shot down over Germany in July 1944 and becoming a prisoner of war. In post-war interviews, Gabreski attributed much of his success to the Thunderbolt's diving capability. Once you understood what the airplane could do, how fast it could dive and how reliably it would pull out, you could set up attacks that were basically unstoppable, Gabreski recalled. I'd climb to 32 or 33,000 feet, wait for Germans to appear below, then dive on them at speeds they couldn't match. By the time they realized I was there, I was already in gun range. They'd try to dive away, but I was faster. They'd pull up, but I could zoom climb faster than they could run. The secret was trusting the airplane. You'd dive until you thought you were going to die, until the ground was filling your windscreen, and every instinct told you to pull out. But you'd hold the dive just a few more seconds, get into perfect gun range, fire one good burst, then pull out. The G-forces were incredible. I'd grey out almost every time, but the airplane always pulled through, always brought me back. By late 1944, the Thunderbolt's reputation among Luftwaffe pilots had transformed completely from the early days when German pilots had mocked the fat American fighter. A captured Luftwaffe document from November 1944, recovered from the headquarters of Jagdgeschwader 3, provided guidance to German pilots on engaging American fighters. The section on the P-47 was grimly candid. The Thunderbolt is the most dangerous American fighter when it holds altitude advantage. Its diving speed exceeds all German fighters by significant margin. Pilots must avoid situations where Thunderbolts can dive on them from above. If caught in such situation and Thunderbolt begins diving attack, do not attempt to escape by diving. The American fighter will catch you and destroy you. Recommended evasion. Brake into a hard climbing turn at maximum G-load. The Thunderbolt's weight prevents it from following this maneuver. Extend the climb until the American breaks off or expends energy. Be aware that experienced Thunderbolt pilots may anticipate this maneuver and position for a second attack. If possible, avoid combat with Thunderbolts entirely, unless holding clear numerical and positional advantage. This document represented acknowledgement of tactical defeat. The Luftwaffe, which had dominated European skies from 1939 through early 1943, was advising its pilots to avoid combat with American fighters whenever possible. The industrial dimension of the Thunderbolt's success was as significant as its technical capabilities. Republic Aviation's production facilities at Farmingdale, Long Island, and Evansville, Indiana, produced 15,683 P-47s during the war. Peak production reached 563 aircraft per month in March 1944. Each aircraft represented an engineering marvel. The wing structure alone contained approximately 3,000 individual parts, machined to tolerances of 1,000th of an inch, assembled by workers who had never built aircraft before Pearl Harbor. The Pratt & Whitney R2800 engine consisted of 2,400 components, each manufactured to exacting specifications. American industry produced these complex machines in quantities that defied comprehension. By comparison, total German production of Messerschmitt Bf 109s throughout the entire war was approximately 33,000 aircraft. Total Focke-Wulf Fevue 190 production was approximately 20,000 aircraft. Germany's production advantage in fighter numbers was overwhelmed by American production of bombers, transports, trainers, and other aircraft types. More significantly, American aircraft reaching operational units were consistently maintained at higher readiness rates than German equivalents. Spare parts were abundant, maintenance facilities were well equipped, mechanics were properly trained. A typical American fighter group in late 1944 could maintain 70 to 80% of its aircraft in combat-ready status. Luftwaffe units were fortunate to keep 50% operational. The training dimension was equally lopsided. American pilot training programs graduated over 30,000 pilots annually by 1944. Each received 400 to 500 hours of flight training before entering combat. German pilot training, constrained by fuel shortages and lack of aircraft, declined to 100 hours or less by war's end. This meant that American pilots arriving in Europe were better prepared, more skilled, and more confident than their German opponents. When flying an aircraft that could dive faster and pull out more reliably than anything the Germans had, this training advantage became decisive. The final months of the war saw Luftwaffe resistance collapse completely. Fuel shortages grounded most German fighters. Those that did fly were operated by inexperienced pilots, who stood little chance against veteran American squadrons. The Thunderbolts' diving advantage, so critical in establishing air superiority during 1943 and 1944, became less relevant as organized German resistance ceased. But the legacy of the Thunderbolts' diving capability extended beyond its role in World War II. The engineering lessons learned from creating an aircraft that could survive terminal velocity dives informed post-war fighter development. The recognition that structural strength could be a decisive tactical advantage influenced American fighter design for decades. The F-86 Sabre, America's first successful swept-wing jet fighter, incorporated structural strength far exceeding minimum requirements, allowing it to dive at speeds approaching the sound barrier while maintaining control. This capability proved crucial during the Korean War, when Sabres faced Soviet MiG-15 fighters in high-speed combat. Later fighters, including the 4 Phantom and 15 Eagle, continued the philosophy of structural overbuilding. American designers consistently prioritized strength and reliability over theoretical weight efficiency, creating aircraft that could survive punishment and perform maneuvers that would destroy more lightly built opponents. In 1987, at a symposium on World War II aviation held at the Smithsonian National Air and Space Museum, surviving Thunderbolt pilots gathered to share their experiences. Among them was retired Colonel Robert S. Johnson, who had survived being shot up over France in June 1943 and went on to achieve 27 confirmed victories. Johnson, asked about the Thunderbolt's most important characteristic, didn't mention its firepower or range or high-altitude performance. He talked about diving. The airplane's ability to dive faster than anything else in the sky and pull out reliably every time gave us a tactical advantage that was almost unfair, Johnson said. We could dictate every engagement. If we wanted to fight, we'd dive on them, and they couldn't escape. If we didn't want to fight, we'd dive away and they couldn't catch us. German pilots were brave, skilled, experienced. They had good airplanes, but they couldn't compete with the physics of a 7-ton fighter built to survive 12G pullouts. We'd dive at speeds that would kill them if they tried to match us. We'd pull out with G-forces that would tear their wings off, and we'd do it over and over, all day long, because the airplane was built for it. I think what really defeated the Luftwaffe wasn't just numbers or industrial capacity, though those mattered. It was that we showed up with an airplane that could do things they didn't think were possible, and once we figured out how to use that capability, they had no answer for it. The final statistics of P-47 operations in Europe revealed the complete transformation from the troubled introduction in early 1943 to total dominance by war's end. Thunderbolt units were credited with destroying 3,752 German aircraft in aerial combat. An additional 3,315 aircraft were destroyed on the ground during strafing attacks. Ground attack operations accounted for even more impressive numbers. Thunderbolts destroyed 9,000 locomotives, 86,000 railway cars, 6,000 armored vehicles, 68,000 trucks, and countless buildings, bridges, and installations. This versatility, the ability to dominate aerial combat, then transition to devastating ground attack, made the Thunderbolt arguably the most effective fighter-bomber of the war. The kill ratio achieved by Thunderbolt units improved steadily throughout the war. In the first quarter of operations, April through June 1943, the ratio was approximately 1.5 to 1, barely favorable. By the final quarter of 1944, the ratio had improved to 4.6 to 1. This improvement reflected both better pilot training and tactical evolution, exploiting the Thunderbolt's diving advantage. Loss rates told a similar story. In early operations, Thunderbolt groups lost approximately 3% of aircraft per mission, unsustainably high for long-term operations. By late 1944, loss rates had declined to less than 1%. Aircraft returning from missions showed remarkable battle damage tolerance, bringing pilots home despite damage that would have destroyed other fighters. The Thunderbolt's combat record in the Pacific Theater, though less well known than its European operations, demonstrated the same diving advantage in different tactical circumstances. The Japanese air forces, flying even more lightly built fighters than the Germans, found themselves completely outmatched when American pilots employed high-altitude diving tactics. Japanese ace Saburo Sakai, who survived the war with 64 confirmed victories, encountered Thunderbolts over the Philippines in late 1944. In his memoir, published in 1957, Sakai described the Thunderbolt as unlike any American fighter we had faced. Our Zero could outturn it easily. But the American pilots would not engage in turning combat. They would dive from high altitude, attack at incredible speed, then zoom climb away before we could respond. We shot down very few Thunderbolts. They shot down many of us. The engineering achievement represented by the P-47 Thunderbolt extended beyond any single characteristic. It was the integration of power, structure, firepower, and systems into a coherent whole that could perform missions impossible for other aircraft. The diving capability was one element of this integration, but a critical one that enabled tactics which ultimately helped achieve air superiority. Alexander Kartveli, the designer who created the Thunderbolt, rarely spoke publicly about his work, but in a 1962 interview with Aviation Week magazine, he reflected on the design philosophy that produced the aircraft. We were asked to create a high-altitude interceptor. I decided to build an aircraft that could survive anything combat could deliver. Not the lightest fighter, not the most maneuverable, but the strongest, most durable, most reliable. Many critics said it was too heavy, too complex, too expensive. But pilots who flew it in combat understood what we had created. An aircraft they could trust completely. An aircraft that would bring them home no matter what happened. An aircraft that could dive at speeds that terrified the enemy and pull out safely every time. That diving capability was not accidental. We calculated the loads. We tested the structures. We knew what the aircraft could survive. When pilots learned to trust those capabilities and employed them tactically, the Thunderbolt became one of the most effective fighters of the war, not through any single brilliant feature, but through reliable excellence in every aspect. At the National Museum of the United States Air Force in Dayton, Ohio, a restored P-47D sits in the World War II gallery. The placard beside it lists specifications, combat record, and historical significance. But visitors who read carefully find a small notation that captures the essence of the Thunderbolt's tactical advantage. Maximum dive speed, 550 miles per hour. Service ceiling, 43,000 feet. Maximum G-load rating, 12 Gs. These numbers, dry specifications to casual observers, represented life and death to pilots who flew combat missions over Europe. The ability to dive at 550 miles per hour meant catching any German fighter attempting to escape. The 12G rating meant pulling out of those terminal dives reliably, safely, repeatedly. Together, they meant controlling the vertical dimension of aerial combat, absolutely. German fighter pilots learned this truth in the skies over France and Germany throughout 1943 and 1944. The heavy American fighter they had initially mocked became the aircraft they feared most, not because it could turn or climb or accelerate better than their fighters, but because it could dive faster than they could fly and pull out from dives that would kill them. The psychological impact was complete and permanent. Luftwaffe pilots who survived the war carried memories of Thunderbolts, diving from above at impossible speeds, catching German fighters in what should have been safe escape maneuvers, destroying them with concentrated machine gun fire, then pulling out of dives that seemed suicidal and zooming back to altitude for another attack. October 12, 1943. Werner Strabe, the Staffelkapitän, who had confidently led his Messerschmitts toward the bomber stream that morning, did not survive the war. He was killed in December 1944 during a combat mission over western Germany, shot down by American fighters. Squadron records don't specify whether they were Thunderbolts, Mustangs, or Lightnings, but the tactical doctrine he had relied upon that October morning, the confident belief that German fighters could always escape by diving, had been proven fatally wrong within minutes of his transmission to his pilots. The Americans learned their heavy fighter could dive, and the sky changed forever. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.